Okay, let's get started. Sorry about that delay. All right, so today, looking forward, this week, we've got Lab 9 started, so I guess we've bumped up that input modeling report to be due today, as opposed to Sunday. So hopefully that extra time was a little helpful. Not expecting a lot from the input modeling report, just really want to see their key points. What's your system? Why did you pick the system? What are the inputs, decision variables, and outputs? And then show me that you have access to the system. So go out and maybe gather some data on some of those inputs, not all of them, just one or two, and then show me that you can do the input modeling for those. And so you're kind of clear to me that you're on your way to where you are about ready to start building the system in Arena, and you have access to data to start parameterizing those models in Arena. So that's kind of where we want to be. I will then take what I get from tonight and as quickly as possible read through those, whatever, 12 or 13, and then notice if there's any red flags, like this looks like it might be a little too simple for a final project. This looks like it might be way too complex for what you need. Then I'll give you that feedback back, and then after that, you'll be on your way. This week, Lab 9, we'll be talking about the output analyzer, which we're going to start talking about in this unit as well, and that will help you do things like analyze rigorously the outputs that are coming out of your simulations, so you can start, validating and running general analyses. And then Lab 10 might be a good one to just flip ahead to take a look at. Lab 10 is, remember there's a drop policy. So I think it's like drop your 2 labs. And so if you've already done a lot of the labs, a lot of people, I see a lot less people doing Labs 9 than Lab 10. Lab 10 though is actually kind of like a super lab. It's like it's graded out of 30 points, but there's 50 points possible. So there's like a bunch of bonus points on that. So there's almost like, it's like 10 and a half. It's almost like a lab 11 is baked into it. And I do that because I want to give people at least the opportunity to get exposure to some other kind of really cool Arena constructs, again, like signals and holds, batching, things like that. That we'll talk about in Lab 10, which will be useful for some of you in some of your models. So Lab 10 is also an opportunity to catch up on any lab points that you'd like to make up. So you might consider that when you're kind of planning out which labs to do. Lab 9 should be very practical for your final project. And then Lab 10 helps you kind of see kind of other things you can do in Arena. Then after that, we have no other labs, but I think there's 2 other weeks left. And so those weeks, you basically can focus on your final project instead of doing the lab. So the next deliverables after the input modeling report are going to be that presentation video and that final report, which are due the Wednesday of the last week of classes. So that's before finals week. And then between Wednesday and Saturday, you will then watch the presentation that was assigned to you and the final report that was assigned to you, and you'll just use a rubric that's on Canvas and you'll evaluate those. So then in finals week, I will then aggregate all of the peer reviews and then review the presentations and reports myself and come up with a grade that balances the 2 of those together. So it'll be an opportunity for you to give feedback to your peers and also maybe reflect on your own presentation and looking at how other people did their presentation. Otherwise, there's only a couple of other ICAs left over this semester. So there was J1 that was due today. J3 and L are the last 2 kind of novel ICAs. And then the only other ICA after that is ICA M, which is meant to be kind of a final exam review, kind of like we did before the midterm. Homework G3 should be due soon. We've kind of covered all of this stuff already. So kind of the chi-squared on the generic distribution, in this case of Poisson, both with an estimated and a given parameter. And then output validation, you're going to do a paired Ttest and then a power analysis. And there's extra help online. And then our last lecture, we talked about the paired Ttest and the power analysis broadly. And then we did a power analysis in the lecture before that as well. And And it says here, the final homework is assigned next lecture. It may already be available. I'd have to double check that, but it definitely should be available by J2. And so this final homework has actually got a little bit of arena on it as well. And so this will bring back the Bucky inventory model, and you'll be asked to do some modifications and some analysis of it in a homework setting. So that's the last homework. And those are kind of all of the assignments that we've kind of gone over there. So you've got the presentation and the final project report coming up. You got these 2 to 3 ICAs coming up, and then the homework that's out, and then the last homework. And that's really all we've got until the final exams. And the final exam will again be a 2-stage setup, where Thursday, the week before finals week, stage 1, and then during finals week, technically Tuesday, but we'll do the whole 24-hour thing, stage 2. So any questions about timeline or anything going forward? Okay. All right, so last time I was introduced this kind of figure where it kind of summarizes hypothesis testing in this so-called confusion matrix, where if you took 100% of the things you threw at a hypothesis test and you took all the decisions it's made, then of that 100%, they would get sliced up into false positives, true negatives, and false negatives. And we talked about where do those come from. And if you have a hypothesis test is always going to have a null hypothesis, which is kind of like what you would expect if everything was running normally. You know, what would this kind of the background expectation be? And that's kind of this blue curve. And we measure a statistic, and that statistic gives us a single number that we know that under the normal case will fall under, by the usual case, the null case will fall under this blue curve. And so when we take a measurement, we have to sort of say, do we think that measurement came from the blue curve or some other curve? And so if the red curve is an alternative thing that could have generated that measurement, then there's overlap between the two of them. And that's what creates the errors in here. And so this basic idea of setting a fence post, where you say any measurement that is to the right of this fence post, we're going to call weird, and to the left of this fence post, we're going to call normal or null, ends up setting up where you're going to be in terms of false positives and true positives. And what I hope you can see is that there is a natural trade-off between false positives and true positives. Or you could say there's a natural trade-off between type 1 error and type 2 error. And so if you increase type 1 error, you will decrease type 2 error, and vice versa. Or another way to view it is if you decrease type 1 error, you are going to decrease your statistical power. Or if you want more statistical power, you're without changing anything else, then you may have to increase your type 1 error. So our goal in choosing a good experiment is we fix our type 1 error at alpha, and then we have to say, what is the amount of statistical power we need? And we have control over that by controlling the number of samples that we take, as well as sometimes we can design the experiment to minimize variability. So it's our goal to make this trade-off kind of as light as possible, so that this curve is kind of as close to this right angle at the top of this curve as possible here. So that's kind of our goal when we design experiments, but we don't have the budget to take millions of samples. And so we're always going to be stuck with this trade-off here. So that's kind of was the general summary for all hypothesis testing, and how this kind of folds into us deciding how many replications do we run, things like that. And so if we look at like popular hypothesis tests that you're using on your homework, that you may use in your final project, the Ttest comes up. Ttest is a great way to take a little bit of data and test whether those data may have come from a hypothesis or not. There's a question here, so we can get 50-30 on it. Oh yeah, so there was a question I think about lab 10. Yes, you could get 20 extra bonus points on lab 10 because there's 50 points possible, but it's graded out of 30. So yeah, lab 10 is meant to provide a little extra lab bonus at the end of the semester for those who want to take on that. So sorry I missed that question earlier. And so, but the key point with, so you go into a T-test when you have a bunch of data, you think might be drawn from a distribution with a given mean, and you want to test against that hypothesis. The mean is the hypothesis. And so you take an average of all your data and you compare that to your hypothetical average. But the key point with a t-test is that you cannot apply the t-test unless you know the samples are independently drawn and you design your experiment to enforce independence. So if you're surveying people, you try to make sure that one person doesn't talk to another person. So the answer from one person doesn't end up influencing the answer of another. And then also drawn from a normal distribution. And so in this case, if you take a bunch of data, you often have to use another test to first validate that your data come from a normal distribution. And then once you've done that, then you can move forward to the t-test. In simulation studies, a lot of the variables we look at come from sums in our simulation, and they are naturally normally distributed. So this we often get for free, as we'll talk about a little bit today, but this is really important if you get a data set in your workplace or something like that. Before you can just apply a t-test, you really have to make sure that it's normally distributed. And given that it is, then you get these t distributions for the test statistic. So under the null, you would expect, based on the number of samples that you have, so whether you had, so these are degrees of freedom, so the number of samples are one more than the degrees of freedom, then you get these different curves. And so with only 2 samples, then that t statistic under the null distribution will have this probability density function. And if you had 3 samples, it'll have this slightly higher one. If you had 6 samples, it'll have this slightly higher one. And if you have a very, very large number of samples, it's a standard normal. And so a t-test is just the extension of a z-test or a z-score to low numbers of samples. That's all a t-test is there. But you can't use a z-score unless it's normally distributed, and you can't use a t-test unless it's normally distributed. We have 2 types of t-tests. We have a one-tailed t-test where you're only focusing on differences that are on one side of the distribution, but we never, ever, ever, unless given special permission, use a one-tailed t-test. So it's very, very rare for us to be okay with differences on one side, but not the other. So you're almost always using a two-tailed t-test, and that's the reason why the threshold values we look up, the threshold values in the back of the book are often for one-tailed, but we need a two-tailed, and because it's symmetric, that's why we have to divide the alpha by 2. So we're always interested in values on both sides. So if something deviated from the normal this way or this way, we would want to flag that either way. It's very, very rare for us to ever get into a point where we'd say, well, we really only care about deviations from the normal that are positive. If you can deviate from the normal, from the null negative as much as you want, even though this t distribution is coming down that way. So we almost never actually use a one-tailed, but we list the data in these tables as one-tailed. That's the reason why we cut the alpha in 2. That way we end up grabbing both tails. So it's kind of the 2 things there. And so what does that end up looking like? So if we have our null hypothesis in blue and we have an alternative hypothesis, what I've done here is I've said we've got 2 data sets that are both normally distributed, that both have the same standard deviation, but one of them has a mean that's shifted up by 2 units in whatever the mean units are. And so I've calculated the t statistic under the null, as well as the t statistic with 2 units up. And I get that picture that I just kind of showed you in that cartoon, where I get these t distributions that are lined up with this overlap. And I need to choose a t statistic threshold to say, when I get data, if it's below 0, I'm going to call it the null. If it's above 0, I'm going to call it the alternative. And so I need to choose what that threshold should be. And so that's what the back of the book does, is it says, well, if you want an alpha of 0.05, set your threshold to this value, whatever it be, 1.96, for example. So, it would be over, if this is 5, 2 would be somewhere like around here. So that's kind of the picture that we get here. Now, if I want more statistical power, I can add more samples or I can decrease variance. So this is with a 4 samples. If I were to sample more than that, say with 20 samples, and then recalculate all of these things, then my null stayed in exactly the same place. But this alternative, given that this is a case where my alternative hypothesis is just the null plus 2, it got shifted over so there was less overlap. So that happened because the kind of distance between these two, if you calculate the distance between these two t statistics, is the difference in their averages divided by their standard deviation divided by square root of n. So the more samples I get, the more I push these curves away from each other and less overlap they get. So that in sample space is what's going on as you're taking more samples. You should go from 20 to 30, then you get almost no overlap there. If I go, so that's what I'm getting is I'm adding more samples. If I have a way to decrease standard deviation, I can do even better. It's, well, how could you decrease standard deviation? That's a property of the population. Well, we can control for certain aspects of the population. So we can say that we're looking at the difference, this Ttest here, maybe we're looking at the difference that's caused by a particular factor, a particular thing that we're interested in, temperature or whatever, but we know that there's variation caused by something else. If we can go into our experiment and manage to remove the variation caused by the thing that we don't care about, then we'll end up reducing variation where the variation left over will be more focused on just the thing that we care about. So we care about temperature, but we don't care about humidity. Well, if we control for humidity by maybe designing our experiments so that we have very tight control over humidity, or we take humidity information and we somehow subtract that humidity variance from the data we have, then we have the ability to reduce the variation in the leftover data that we have. And that allows us to bring our standard deviation down. And we will see ways in which we do that in some of the final lectures of this class. There are variance reduction techniques, VRTs, that we apply to simulation methods that do exactly this, where we can reduce the variance in our samples. And that moves these farther apart and makes less and less overlap there. So that's kind of our goal, is that if we're stuck with a test, the way we get more statistical power is to take more samples or to decrease variance. And we have certain standards for statistical power. We want 80% or more statistical power. So we would like to design our experiment to either take enough samples or decrease the variance enough to give us 80% statistical power. And we always have to know that before we do the experiment, before we spend the money that we budgeted on that experiment. And if we can't do that, then we might need to find a new statistical test, or we might need to go back to our stakeholder and say, for the particular test that we can use for these data and for the budget we have for our experiment, the best we can do is discriminate to this resolution. And so the answer that I'll give you might be that the data you have are close to the null, but I won't actually know that they really, but close to the null might actually be a giant window, which, so like if I were to go back in my low statistical power case, do you imagine this is a very low statistical power case? You can say that because there's so much overlap between the alternative hypotheses and the null hypotheses, then I can't actually reject the null. But if I were to accept the null, what I really am doing is accepting the null plus or minus a large window around these two. And so statistical power reduces your need to have to do that by separating these two things up. So that's kind of what we're doing when we're choosing numbers of samples. All right, so are there any questions about this general visualization about what's going on when we apply a t-test and where statistical power comes from, where the false positives, where the false negatives come from? This conceptualization of these statistical tests makes sense. Okay. All right. So far we've been talking about parametric tests. And so this is a term that you should remember. This is an important kind of definitional term, parametric versus non-parametric tests. So a parametric test is a test like the t-test that is only inferring parameters. So in the t-test, we assume normality. So we assume that the data are normal. We assume that an alternative hypothesis has the same standard deviation as the null hypothesis. So we take that for granted. We say, so we have to do other tests to make sure that we can even make those assumptions. But given that we are comfortable making those assumptions, then all the t-test does is says, well, what's the mean of the distribution? So you know it's a normal distribution. You know that you have an idea that the null hypothesis and any alternative are going to have the same standard deviation. So really all you're inferring is, well, then what is the mean of that normal distribution that you assume is there? And that's what we mean by a parametric test. It is making an inference about a parameter, just a parameter, taking everything else for granted. Now, when we can't take everything else for granted, then we have to use non-parametric tests. And so these are tests that actually make an inference on the whole distribution. So so it's like in a t-test. So for example, like a t-test, I had to assume that both normal and any alternative are both null and any alternative are normally distributed. A u-test, which is the non-parametric version of a t-test, doesn't make any of those assumptions. It says your distributions can be anything. Your null distribution could be anything, and your alternative distributions could be anything. And I am going to test whether their medians are likely to be the same. And so it in some ways is a much more flexible test. The downside with such a test that makes no assumptions going in is that it has far less statistical power. So if you can reject a null with a non-parametric, you're fine. But if you fail to reject a null with a non-parametric, you often have very little data. If you can reject if you fail to reject a null with a parametric, you're often in much better shape to work towards saying, okay, well, actually, maybe that null really is the right explanation, but not so much here for the non-parametric. So you lose power, but you don't have to make any assumptions going into it. And so all of the tests that we've talked about, t-test, paired difference t-test, ANOVAs, these all require normality, but if you were to Google for non-parametric t-test, non-parametric paired difference t-test, non-parametric ANOVA, you would end up finding out that there are non-parametric versions which work exactly the same way. So in JUMP, you'd find them there, and they're set up the same way. Like, here are my 2 columns of data. Apply this Wilcoxon signed rank test. So anywhere in JUMP where you could apply a paired difference t-test or a paired t-test, you could also apply a Wilcoxon signed rank test. And you'll get, it'll run fine, and you'll get p-values out. But this one will have less power than this one. But this one you'll be allowed to use on a wider set of data sets than this one. A program like JUMP is not going to check to see if you're allowed to use a paired t-test. It's just going to run it. It's up to you to see, do my data meet the assumptions of a t-test? And if they don't, and you have no other way to deal with it, then you have to go down and use this other test. So I'm not going to quiz you over all of these different non-parametric tests, but I do want you to know the difference between a parametric test, where you're inferring a parameter, and a non-parametric test, where you don't make any assumptions about the distribution, and you're really making an inference about the distribution itself. And I want you to know that, because there's going to be times in your statistical career where you are not going to be able to use the parametric test that maybe is burnt into your brain, and you have to know, well, what's my alternative? And you got to know to do that Google for what is a non-parametric ANOVA, and then you'll see, and then eventually you'll remember a Kruskal-Wallis test. But the first couple of years of your career, you're going to have to do that Google every single time you need the non-parametric ANOVA, until it becomes second nature that, oh, that's a Kruskal-Wallis. And unfortunately, they're all named after these old historical figures, which I think makes them even harder to remember. So But things like Ttest and Utest, I think those have kind of a natural correspondence. The rest of this, yeah, you just got to memorize it. And then on top of all of that, we have a term exact non-parametric, and an exact non-parametric makes no additional simplifying assumptions. And so a non-parametric test says, I don't assume anything statistically. It doesn't have to come from one distribution or another, but like the chi-squared test, I might still assume that I have expected values in each bin greater than 5, or greater than or equal to 5. And an exact non-parametric method, you can really just apply it to anything without any assumptions whatsoever. There's no simplifications. So I mentioned here, chi-squared is not exact, but Kolmogorov-Smirnov is exact. And that's because the chi-squared requires that greater than or equal to 5, whereas the KS test can really be applied anywhere. So generally a good heuristic here is that the more flexible the test, the less power it has. So if you really need statistical power, you're probably going to need to make assumptions about your data. If you're not worried about statistical power, if it's really about making sure that you're, it's really about testing, rejecting something, then sometimes it's okay to throw out all the assumptions. So if regardless of which types of tests you do, if you do ever want to confirm, like in a goodness of fit sort of thing, with a parametric or a non-exact test. Before you, so this is just me saying, make sure you apply a Shapiro-Wilk, do your QQ plots, whatever, to make sure that you meet the assumptions of the non-parametric or the parametric. But then the other thing I wanted to add here is that if you ever are trying to show that a null is true, or trying to accept the hypothesis, then finding another source of evidence to help you confirm that is also a good thing, like a QQ plot. So it's always hard to accept a hypothesis, and so you might need to build up more evidence to make that argument. All right, so any questions about that, about the differences between a parametric and a non-parametric test, or a non-parametric test and an exact non-parametric test? This will become, I think, a little more clear as we go forward as well, but at least now we've at least learned enough where these terms can make some sense. Okay. All right, so if I were to do the same sort of exercise I did with the T-test, with the chi-squared test, this new little numerical simulation, what I can do is I can say, well, I went and I simulated I generated a bunch of data where I sort of said, well, what if I have what probability did I end up using here? An expected count. So I have 100 samples with a 5.5% probability of them landing in a bin. So 5.5% of them come in the bin, the rest of them go in another bin. And so that I can describe with a binomial distribution. So a binomial distribution with n equal 100 and p equal 0.055. Those are the blue stems here. So that's the probability mass function for the binomial distribution. I've got the expected value. You can see it's roughly in the middle of this thing, shift a little bit over because of the tail. So that is binomial distribution. This is an exact characterization of where we would expect things to fall if they were drawn, if a coin was flipped along this way. Now, if you notice here, this is kind of hump-shaped here. And so that's kind of going to be the hint that we end up making use of to get to the chi-squared. So the idea here is if in each one of these plots, I have 100 coin flips, but I have different weights on the coin, on how often it comes up heads or tails. So here you can view it as it's coming up heads 5.5% of the time. And so this is the number of heads I get in any 100 coin flips. That's one way you could view it here. So here you can imagine that I've got the, for 100 tosses, here, this is the distribution when it's only expected that one of those will come up heads. Down here, this is the distribution when 6 of them are expected to come out heads. And so as we can see, the binomial distribution, that's the stems in each one of these plots, as the expected number that comes up heads gets larger and larger, the binomial distribution goes from being kind of a sort of a peak on the left-hand side with kind of this long kind of tail, very skewed distribution. It starts getting a little bit more hump-shaped and moves itself away from 0. And so by the time you get 5, it's pretty darn hump-shaped. And then 6, it's pulled pretty far away from 0. And so what we're seeing here is the convergence of the binomial distribution to a normal distribution. So the solid line that I've plotted on top of the stems here, that is the normal approximation for a binomial. And it fits okay for each one of these, but notice that a lot of the normal distribution is buried in the negatives. It doesn't finally kind of get to the point where a small amount of the normal distribution gets truncated until about 5. So and once we're at 6, then we can see nearly all of the mass of the normal distribution is positive, and it's landing right on top of the stems. So this here, I was saying last time, is actually seeing the central limit theorem in action here. So if you view every time you flip a coin, it comes up 0 every time, or under tails, 1 is heads, and you add up the 1s and 0s, then you're just creating a sum of 100 random variables. And we know that sums eventually are going to look normal if they're independently drawn. And that's what we're kind of seeing here. And this empirically is showing us that when the expected number of heads reaches 5, that's kind of the point where we can finally give up on the binomial and just embrace the normal as our approximation. And this is where this is where our assumption in the chi-squared of each bin having an expected count of 5 or higher comes from, is that the chi-squared derivation requires us to be able to swap out a binomial and put in a normal. And you can only swap out a binomial and put in a normal if the expected count is 5 or more. And so that's where that comes from. So in order to make your use of the chi-squared exact, would be kind of one way to say that, then you have to make sure that you've got this 5 count. And so the idea here is if each of my bins, each one of my counts of my bins can be approximated as a normal, then I basically can standardize them. So I can then, I can take each one of those bins and I can subtract off the mean for that bin. I can divide by the standard deviation of that bin, and every bin in my chi-squared test can be represented by a standard normal, so sort of a z-score. And I can then add up all of those things together. So that'd be one way to view it, or I could square them and add them up. And that's perfectly fine too. So if I view the z-score in each bin as kind of a deviation from the expectation of that bin, if I want to say, well, what's the deviation across all the bins? Well, if I square them, then I'm going to have a positive number for all of the bins. And so if the bins are dead on where they're supposed to be, they'll be 0. And if you sum them all up across all the bins, it'll be 0. But if if they're -3 or +3, if I square them, then it's going to be 9 either way. So what the chi-squared does is it squares each one of those z-scores so that we can sum them up together. And then the chi-squared statistic is just the sum of squared normals. And so when I look for the chi-squared distribution with a degree of freedom of 1, well, that is just that's the distribution of a standard normal that's squared. The chi-squared statistic with a degree of freedom of 2, that's just 2 standard normals squared and added together. And so that's the interpretation of the chi-squared. And that's the reason why, even as the chi-squared's degrees of freedom gets high, now you're adding up lots of standard normals, which is the reason why the chi-squared starts looking hump-shaped itself, because it will then get, the central limit theorem will catch it up, and then eventually the chi-squared test will look like a normal as well. So that's where our assumptions with the chi-squared come from, is that we are approximating the counts found in each bin from a binomial to a standard normal, squaring them so we can add them all up together, and then modeling what the null expectation would be if it was just the sum of a bunch of squared standard normals. And that's where we get this distribution. And increasing the degree of freedom or increasing the number of bins increases our tolerance for error. And so in other words, the statistic that corresponds to an alpha of 0.05, that critical statistic is going to get larger and larger as the number of bins gets larger, because we're sort of saying that, well, yeah, if we have more bins, we're just naturally going to accumulate more error. And so we need to allow for more error. And so that's what's happening as you go from 1 degree of freedom to 5 degrees of freedom. Then this, the p-value, that's what I've plotted here, corresponding to the particular chi-squared test statistic, ends up having this kind of pattern where it's going up. And that just corresponds to this idea that the critical chi-squared statistic allows for more error when you have more bins. And that's just fair. You know, you've got more opportunity to make error, so you're going to add that thing in to get the same alpha value. And so that's where we get this chi-squared. So what I did is I simulated, so I have a null expectation here. That's my chi-squared statistic. That's the dark line. The blue bars are me simulating outcomes. So I basically said so I've got 29 degrees of freedom here. So that's 30 classes. So I went into MATLAB and I said, let's just draw a bunch of data that could come, some of it's going to land in class 1, some will land in class 30. So where it lands in one of these classes, that's going to be randomized. But I created a probability distribution, and my null probability distribution is this chi-squared distribution here. But then I perturbed it just a little, and that gave me the blue bars. And then I perturbed it a lot. So whereas maybe in the null distribution, none would have showed up in class 30, but in this highly perturbed one, a bunch showed up in class 30. And then I just did a histogram of those things. And what we can see is if my distribution is close to my null, then it almost slots right into underneath the chi-squared. But if the distribution is way different from the null expectation, then I get this thing that's just way far away from the original chi-squared. And so this is what ends up generating that chi-squared statistic, is I'm effectively measuring the difference between this expected value, this expected probability density of the chi-squared, and the actual values here. And when they're very far off, then I'm going to flag that as being unlikely to have come from the null, from my expected distribution across these 30 classes. So that's what's going on there. So this distribution, which is necessarily one-sided, is exactly the distribution that we see, if I have my next slide, in that cartoon where I've got the hypothesis test with the red distribution and the blue distribution next to each other, and the overlap is where you get the false positives and false negatives. The distribution that applies there for a chi-squared is a one-sided distribution where it's almost never zero, and then it goes off in one direction. And because this is the one case where it is a one-sided test, and there is no such thing as a two-sided chi-squared test, that's the reason why we don't divide by alpha by 2 like we do with the t-test. But still, it's the same basic interpretation. I have an expected distribution of chi-squared values, and based on the actual chi-squared that I calculate from a distribution, then the question is, how well does it correspond to the expected distribution that I get here? So the solid line is the chi-squared values I should get under the null. The blue bars are the chi-squared values I do get from a slightly perturbed distribution off the null. The red bars are the chi-squared values I get from one that's highly perturbed off the null. So it's highly unlikely that these values will show up underneath this big hump here. So I'm very likely to catch this alternative hypothesis as being different, unlikely to catch this one as being different. All right. So any questions about that, about the basic foundations of the chi-squared test? And the big thing I want you to remember is that the expected number in each bin has to be 5 or more. And that is a so-called continuity approximation. That is because the chi-squared test depends upon being able to approximate the discrete binomial distribution by the continuous normal distribution. And so if you do not have that 5 or more, the math behind the chi-squared test just disintegrates. And so that's the reason why that 5 or more comes from that. You know, so why 5? Well, it's those pictures I showed you. Below 5, the binomial distribution really doesn't look at all like a normal distribution. And that's why we really need 5, because below that, none of this math works. Okay. Questions online? All right, so we've talked about a chi-squared test. It's a, when we've been looking for, we've been sort of using it as a goodness of fit indicator. So we've been saying, we expect the distribution to look a particular way. We actually got data this way. Do our data look like the expected distribution? And so, so looking for these differences, well, so this is actually the application we haven't been using. So what I'm trying to say here is that, so we've been using it that way in the goodness of fit sense. We also can use a chi-squared like to look for differences in treatments, kind of like we did with a t-test. And so as an example, you could say, I've got a group of people that wear a particular type of shoe, and I have another people that wear another type of shoe, and I ask them to survey how comfortable they are, and maybe their answers fall into certain bins on a Likert scale, from I really like it to I don't really like it to I hate it. And you look at that distribution, and then your question is, does the shoe change that distribution of counts across those bins on a Likert scale? And you can use a chi-squared test to test for whether the shoe makes a difference to the distribution. And that is a so-called test of independence. So we have been using chi-squared as a goodness of fit test, but the chi-squared test is also used as a so-called test of independence, where you're saying, is the distribution of responses independent of the shoe type? So that's another way we can test that. So if your response variable are count variables, then you can say, does my simulation look different than my real world variable? Because does the count coming out of my simulation have a different distribution than the count coming out of my real world? And you can put those two in together as a so-called, we could say like a 2-sample chi-squared test, and that would test for independence. So that's, again, it's another way of viewing the chi-squared test. So in some ways, it's goodness of fit. In other ways, it's testing for differences. Regardless of how you use it, it's a non-parametric test. It's not exact because it makes assumptions. Out in the real world, lots of people still use chi-squared tests, but if you can't make this assumption, but you still want to use something chi-squared like, there are other tests now, like the G-test is something that works exactly the same as a chi-squared test, but I think you only need like 2 in each bin or something like that. And so the G-test is sort of a more sensitive version of the chi-squared test, but there also are exact tests. And so whenever possible, you try to use an exact test. And so the binomial test is a test that you generate the test statistic actually using the raw binomial, just like I was talking about, like chi-squared approximates binomials and normal, and that makes the chi-squared math easier. If you really only have 2 cases, though, you can just use a binomial test, a raw binomial test. No need to do the approximation, and then you can then that's the better test to use. You can also use a so-called multinomial test for the expanded version when you have more than 2 cases, and that can be a competitor to the chi-squared test. There's also a so-called Fisher's exact test here, which is great for small numbers. And so anything you want to do with a chi-squared test, but you can't because it has really small numbers, then you can say, well, can I use a Fisher's exact test? So I'm not going to ask you to know what all these exact tests are, but I do want you to know that there are exact tests out there that can be applied in the same way as a chi-squared test. So it's important for me that you know there are assumptions that must be true for a chi-squared test. It's also important for me to know that there are alternative tests out there where those assumptions don't need to occur, but you're always giving up a little bit. So for each one of these tests, you might be giving up something that, that you had with the chi-squared test. So statistics is all about trade-offs. How do I deal with this beast that is data? depending on the classes of the data or the type of the data, you like to use the test that provides you the most information for the least amount of cost. And that's the reason why we have all of these different options. But some data sets, some of these options aren't a possibility. So in this class, we really focus on things like the t-test and the chi-squared test. As you move on from this class, you really need to know that those are not the end of the world when it comes to stats, and that you need to be aware that non-parametric tests exist and that other exact tests exist, and you will eventually bump into them. And when you see a Fisher's exact test, you're like, I don't know how that one thing works. Something in your head should hopefully say, oh, right, this is like a chi-squared test. And so it will be applied in the exact same way as a chi-squared test, but it was used because maybe the data just happened to not be of the type that would work with a chi-squared test, but otherwise it solves the same problem. So just wanted to give you exposure to these ones, but again, I'm not going to test you on what is a binomial test, what is a Fisher's exact test, etc. Just know that they exist out there as alternatives to the chi-squared. The alternative that we do talk about in this class is the KS test, the Kolmogorov-Smirnov test, which is an exact test, just like the Fisher's test. No additional assumptions are needed. The problem with the Kolmogorov-Smirnov test is that its critical values get a little hairy when parameters get estimated. So if you have no estimated parameters, just go hog wild and use the Kolmogorov-Smirnov test. But at the point where you estimate a parameter, like you do in your homework, you may have to look up a special version of the KS test for your distribution when there is an estimated parameter. So you're like, I'd like to test the Poisson. If it's Poisson with a given parameter, go forth and do the KS test. But if your Poisson has an estimated parameter, you're gonna have to Google for, is there a KS test that has been adjusted for the Poisson with an estimated parameter? And then you'll look up and you'll say, okay, for that, just use the normal KS test, but use these critical values. So the critical values get a little hairy when parameters are estimated, which is the reason why we can't just use a KS test for everything. And the big thing about a KS test is it tests for differences between distributions, as we kind of all already know. A question that students will give me, well, then how do you develop tests when there are no assumptions that you can make? And the way the KS test works is it uses what mathematicians refer to as a Brownian bridge. So in a KS test, you've got a distribution you expect, that's the red line here, and then you've got an empirical CDF that you get by sorting your data and plotting them against their normalized rank. And so that's the blue steps here. Now, with a KS test, you know that they're both going to start at 0 and they're both going to end at 1. So it's a little bit like they're alternative versions of a bridge. You've got one bridge that's bridging from 0 to 1, and that's the red line. And then you've got another bridge, this is the blue one, which is like an alternative path that you could have made to get across this chasm. And but you know that bridges have to be continuous. And so what mathematicians came up with the KS test is they said, well, if you start at the same starting point on a bridge and then wander away randomly in a drunken walk. So this is a kind of a term mathematicians use, a drunken walk, a Brownian walk. So you step away and you have a probability of stepping back, or you have a probability of stepping farther away. If you do that over and over again, what we know is you eventually have to get back to this point. So that means that Brownian walks that walk way far away, drunken walks that go way far away, they never make it home. So we exclude them from consideration. And we only consider drunken walks that can get from point 0 to point 1. And so of those, we ask in the distribution of those walks, then that becomes kind of our test statistic to sort of see, is the distribution we see kind of close enough to the nominal bridge here? And so that's how the test statistic for the KS test is they sort of say that if we kind of view this as our central bridge, how far away from this bridge can we get by just taking random steps away that guarantee that we still get back? And there will be very few bridges way out here, and there'll be very few bridges way out here, but there will be, most of them will be kind of close to this one here. And so that will form the bulk of the difference here. And so we're measuring the difference between the nominal bridge and the drunken bridge. And that difference, that becomes the distribution. So it's very unlikely for this to be very large if you're on a bridge that manages to get back home. And but it is pretty likely that this will be sufficiently short. And so that's where the Ttest distribution comes from. So this is an example of a Brownian bridge. So since they don't know what the alternative hypothesis is, they use these Brownian bridges as surrogate alternative hypotheses and then say, over all possible Brownian bridges, what's the distribution of the Ks statistic? And that's the one that you use for this goodness of fit test. So that's how the Ks test works. So there really is some mathematics behind it, but it's mathematics that had to be very clever about how they model an alternative hypothesis, given that we're not allowed to assume anything because it's an exact test. The Anderson-Darling is a similar test. There's the Ks. It's built in a very similar way as the Ks test, but it is built in a way that gives it more power. A Shapiro-Wilk test is a test that only tests for normality, but it has an extremely high power. And so if you know you need to test for normality, you use the Shapiro-Wilk. In reality, most people, Ks test shows up a lot, but when you have estimated parameters and things like that, a lot of people just rather use the Anderson-Darling. So again, I actually don't care that much if you know Anderson-Darling, but I want you to have exposure to it, because if you go on in statistics, you're going to see an Anderson-Darling, and in your head, I want somewhere to be a synapse that fires that says, oh wait, that's just like the Ks test, but it has more power. And Shapiro-Wilk is one that I want you to care about a little bit more, because really before you can do any Ttest, any ANOVA, you really have to do a Shapiro-Wilk first. I'm not going to make you do a Shapiro-Wilk in this class, but as you go on where things are a little less sanitized, then it'll be really important to get your assumptions right before you do your T-tests and your ANOVAs, and you're going to need to do that Shapiro-Wilk first. So this guarantees your data are normal going in. All right, so any questions about any of this stuff? So that's my kind of summary of the tests we've been using so far, where they come from, and what alternatives are out there that you might see out in the real world. All right, so when we think about your final project or just modeling in general, we have the random variables, the decision variables, the output variables. These are the things I want you to name in your input modeling report. We've talked about how for input modeling, we choose the distributions here. And then for output validation, we then verify, or we then validate that these outputs look like real world outputs, so that then we can start experimenting with our model, so that when we see differences here, we can be pretty sure that if we did the same experiment in the real world, we'd see the same difference. That's kind of the goal here. Now, when we do those experiments with the simulation model, we'd say, okay, I validated my simulation model is a surrogate for reality. Now I'm going to simulate a change that I want to experiment with. So I'm going to say, well, what if I changed how this restaurant was structured, and I want to see how it changes performance, or if it changes performance, at all, if. And so the thing that, and we didn't get to this last time, but there's an issue here, is that I have to choose, well, what output variable do I measure? Do I measure utilization? Do I measure delay? Do I measure maximum line length? Do I measure all three? Which one do I look for differences in? So I got my baseline case, which, I want to say, okay, so if in the baseline case, I get this utilization, in my new case, for my altered case, my hypothetical case, I get a different utilization. Well, do I only look at utilization, or do I look at these other things too? And so the problem is, if you have a bunch of output variables, if you don't find a difference on one using, say, a T-test, eventually, because a T-test has type 1 error, you will eventually find a difference that may only be due to chance. So you get the fishing problem. So there's a 5% chance you're going to see a difference between your baseline case and your hypothetical case for each output that you measure. And so if you're just generally looking, does my hypothetical case make any difference whatsoever to the model? I somehow need to correct for this fishing problem, because if I'm measuring 100 different things, I'm almost guaranteed to find that one of them is going to be different by chance. So how do I deal with this so-called multiple comparisons problem? So that's what I'm sort of saying here, is that each one of my t-tests that I run independently has a false positive rate. How do I deal with the fact that if I'm doing multiple of these, the false positive rates kind of accumulate? And that's something that the simplest way to deal with that is what we call the Bonferroni correction. And so what we do here is so we recognize that the probability of getting at least one false positive is going to be 1 minus the probability of no false positives, which we know is 1 minus the type 1 error for each individual test to the k, where there's k response variables. And we know that it's easy to prove that this is going to be greater than my desired false positive rate for the whole test. And so I want one false positive rate for my entire test of, is my base case better or worse than my hypothetical case? And so how do I ensure that, that the upper bound on this thing is going to be alpha, which is my desired false positive rate? And the way I do that is my individual tests that I do for each response variable, I can divide them by the number of tests. So the false positive rate for each individual t-test, I can divide by the number of tests I do. And if I do that, if I were to plug this thing into this thing here, then I can guarantee that the probability of at least one false positive for the family, so this is the family-wise error rate, will be bounded above by my desired alpha. So this is the so-called Bonferroni correction. So if I go back to this here, if I want to do a test of my hypothetical model versus my baseline model, I can do a t-test for utilization with an alpha, with my desired alpha divided by 3. And then I do average delay with the desired alpha divided by 3. The maximum line length with the desired alpha divided by 3. And then I can look at those 3 together and I can say, did any one of them detect a difference? And if at least one of them detected a difference, then I say, hurrah, my hypothetical model is significantly different than my baseline model. And I can make that inference with a family-wise error rate of 0.05. So my individual error rate is 0.05 divided by 3, 0.05 divided by 3, 0.05 divided by 3, 3 independent t-tests. But my family-wise error rate will be 0.05 or no greater than 0.05. That's the Bonferroni correction. So if you're looking at multiple outputs, make sure you adjust your individual error rate for the number of comparisons that you do. That's the Bonferroni correction. Does that make sense? Are there questions on that? That's just what I'm summarizing here. Now, if you've got more sophisticated software like JMP, you can find that there are tests built into JMP like the MANOVA, the multivariate ANOVA. Or you can run ANOVAs with so-called post hoc tests, like the Tukey's test or the Fisher's LSD. These are more sophisticated ways that, that handle this exact same problem, but what do you think they give you? Just to test how many people might still be awake after all of this. So here I've got the simple way to deal with the multiple comparisons problem. It works, it will detect differences. But there are these specialized ways that, that are built specifically for testing for multiple comparisons in one shot without having to run multiple t-tests and things like that. Why do you think we have these specialized tests? What do these tests probably give you that this test doesn't give you? It gives you more something. What's the blank there? So whenever we always seek out more of this whenever possible in statistics. More power. These are more powerful tests. And so these tests make fewer assumptions as the Bonferroni correction, and so they give you more power. So if you can, you use a MANOVA, or you use an ANOVA with post hoc, depending on what type of test you're doing, And these are nice alternatives to doing this Bonferroni multiple comparisons thing, because they will detect they will detect differences just as well as this one. But when they don't detect differences, they'll have more statistical power. Because if you notice in the Bonferroni correction, if I have a lot of comparisons, my individual error rate for each one of these tests is going to be super small, because it's going to be 0.05 divided by the number of comparisons. If I have 100 response variables, then it's going to be 0.05 divided by 100 for each one of these. And so now my false positive rate is super, super low for each one of these, which means my statistical power is super, super low. And so I lose out on statistical power through this Bonferroni correction. But I at least keep my false positive rate under the prescribed amount. So, but if I can, I'd rather use a MANOVA or an ANOVA with post hoc. So again, if you've got the software for it, avoid Bonferroni and use the tool that's built for this. But if you just, if you're in a pinch and all you've got is available are Ttest, then Ttest with the Bonferroni correction allow you to solve this problem. All right, so any questions on that? The only other comment I want to make before we do a quick kind of intro to where we're going in this unit is this alpha equal to 0.05 up here. This is kind of, at least in sciences, if these fundamental sciences, a little bit different in medicine, assumed to be the standard that we want here, the bright line standard, alpha equal 0.05. Now, if you work at a well-funded engineering firm and you really are interested in detecting a possible improvement to your process, then you might have the funding that you can change your error rate. You can say, well, you know what, I'm willing to tolerate a higher alpha, because you want to find as many differences as possible. The downside of a low alpha is there will be differences, so potential optimizations that are buried in the data that you might have detected if you had a higher alpha, but because you had a lower alpha, then those things you sort of say, I'm conservative here, that looks like it's too close to the normal for me to really pursue. But if, so for in science, you wrote an NSF grant, you got $500,000 for 2 years or whatever, or 3 years. It funds a single grad student, a couple months of summer salary, and you'll never, ever, ever be able to do this experiment again unless you manage to get other future funding, and nobody else is interested in this problem. So really, the experiment you're going to run over the next 3 years, that's it. You better get it right. So if you find that there is a difference, so if you're making an inference about how nature works, then in that case, you better not find a difference that's fictitious and publish it, because you'll be the only one to have ever published on that, and people will just have to take your word for it, because people won't necessarily go back and reproduce your study. So that's the reason why in science, they might be want it to be 0.05 or lower. For health, they might want this to be 0.01, that might, further down. But in engineering, we often do have R&D budgets where we can run more experiments. So in engineering, you might tolerate a 10% error rate, and then you'll say, look, we found what looks to be a difference here. It had a p-value of 0.07. So the scientists wouldn't call it a difference, but we think there's a trend here that is worth additional investment. And so you then can get IRAD funds, internal R&D funds, to do additional experimentation, to throw more experiments at it, to see if that thing's actually there. So the alpha you use might vary when you're in an engineering case. So engineers often might use a higher alpha, people in healthcare might use a lower alpha, the sciences typically use this alpha. So your choice of alpha often depends upon the stakes. Are there safety concerns? If there are, maybe I need a lower alpha. Are there funding concerns? If there aren't funding concerns, maybe I need a higher alpha. So those are just practical things to think about. In this class, we're going to keep it at 0.05. Just keep it with the scientists, but in the real world out there, this might vary. And just remember this plot, when it varies. So as your alpha gets higher, your power gets higher. If your alpha gets lower, your power gets lower. All right. Questions on that? this will also not just apply to where you set your alpha, but which tests to use. So I mentioned back here, a lot of you who go on into stats will do a lot of ANOVAs, and you'll follow them up with post hoc tests. And there's a bunch of post hoc tests you can pull up and say jump. You can pull up a Tukey's test, you can pull up Fisher's LSD. ANOVA even has a Tukey's test or Fisher's LSD. Scientists use a Tukey's test. Engineers use Fisher's LSD. Why? Because Fisher's LSD happens to have a higher type 1 error, which scientists don't like. But engineers hate the idea of missing out on a potential optimization they could spend more money developing and then turning into something that is commercializable. Scientists don't care about commercialization. They really want to find what's true, and so they're more conservative. So this is the conservative post hoc test. This is the more, I don't know, liberal or more adventurous post hoc test. And so if you ask an engineer what post hoc test to use, they'll say LSD. If you ask a scientist which post hoc test to use, they'll say Tukey test. And if you're a student, it'll be confusing because you'll say, well, which one's the right answer? Well, the context matters. Engineers care less about type 1 error. That's why they use LSD. Scientists care a lot more about type 1 error. That's why they use Tukey tests. So that's also what I'm kind of trying to communicate here, is that the alpha you tolerate will depend upon the job that you're working. Okay. So questions or anything, comments? All right, so I just want to take the last couple moments. Well, we can do a attendance question here in the middle for those of you who are hanging out here with me. And let's say the question here will be, what value of alpha will we use in this class normally? So that's just sort of asking what's, although you might use lower values in some contexts, higher values in others. For this class, what value of alpha type 1 error do we generally assume? All right, so now we're in Unit J. And so I'm just going to get started on this, and we'll pick up from where we, next time here. But Unit J is all about dealing with these questions that we have to address in a simulation study. So, what measures of performance are we going to use to tell that one hypothetical setup in a simulation is better than another? Trading off computational time and statistical power. How many replications do I need to run of my sim to make a strong argument? How long should each run of my simulation need to be? If I use more replications or longer simulations, then my simulations are just going to take more time. So I run simulations that take weeks to complete. And so I need to say, are there things that I can do under certain contexts where maybe I don't need as much statistical power, where I can back that off and say, for a pilot study, this only needs to take 3 days. And that helps me get an idea of how the system works. And then for maybe the full study, I have to then dial up my statistical power and then have it run in a couple of weeks. You guys hopefully won't be running sims that take weeks. Hopefully they'll take minutes at most, or maybe, if you're in a really complicated one, an hour or something like that. But so those are, relatively fast simulations. So, and then the other thing, trading off computational time and bias reduction. And so what we'll learn about is that there are certain simulations that introduce a term called bias that we're going to define. And in order to get rid of that bias, you can run the simulations for a certain amount of time where you don't take any data from them. You just let them go through a process that manages to reduce that bias. And so there's going to be a trade-off between the amount of time wasted not collecting data and the bias reduction. And so the more time we throw into bias reduction, the less time we get to actually collect data, and vice versa. So we're going to need to figure out how to manage that trade-off. So really, this whole section is about the trade-offs needed when making practical decisions in simulations. And so we are going to introduce 2 types of systems that we're going to be simulating, terminating and non-terminating systems, and 2 types of simulations that map to those. So terminating systems, which we're going to define, are simulated by transient simulations. Non-terminating systems are simulated by steady state simulations. And we oftentimes you'll see these terms swapped. So someone will refer to a transient system or a terminating simulation, and that's fine with me. Just formally, terminating, non-terminating describe the system, and transient and steady state refer to the simulation. But if you happen to swap them, so because you know that a transient simulates a terminating, you're going to call it a transient system, that's fine. But that's something that we have to deal with here. So what I might do here is just stop here, because this is a good place to pick up on next time. And I'll give you the last attendance question here then. And we'll, and the question that I will give you are, well, this will be easy. What are the two types of simulations? Just leave that up there. And that's all that I have for you today. So happy to take any questions or concerns after class here. I'll hang around for a minute or two. Otherwise, feel free to Slack me or email me or anything like that. And thanks for your patience as we go through all of this kind of, well, probably was dull the first time, but to me, the statistics are really exciting, and I think they will get exciting for you later in your career, just sadly, probably not in this class.